Okay. So, I'll try to get through these. What I may have to sacrifice is there's a link to a video in here of a physicist named David Deutsch, and there's a link to it in the textbook as well, so I may skip past that so that I can catch up with the lectures, but I would encourage you to watch it nonetheless, and I'll point out to you where that is. But I want to start this class with this question: why study science? Why is it important that you're here? And I think that there are a number of answers to this question, more than one. We've got to understand that I understand none of you are going to be scientists, though I have had a couple students in this class decide to become science majors after taking this class, which is very gratifying. But most of you are going to find your careers in other places. You're going to be, lawyers or psychologists or business people, whatever it is. And I've had just about every major possible in here. But all of us live in a technological society, right? The way we live has been brought about by the development of technologies that we all rely upon, that we all enjoy. We wouldn't, have the life we have without these technologies. Our cell phones, the computers and laptops that we use, the plasma TVs, high def, waiting for 3D TV, all that stuff, right? I mean, we all enjoy this life that we're living. We also appreciate that we can go to the doctor and we can expect to get the medication that we need to get well whenever we're sick. We can expect to have a broken bone fixed correctly and so forth. And these are not expectations that we have had for very long. If we think about human history, most of the time we have not lived with that expectation. So we enjoy this modern prosperity, right? There's no question about it. It's come about because of science. It's come about in just the last few hundred years, a couple hundred years in particular, since the Industrial Revolution, really kick-started the development of not only our knowledge of the world, but our application of that knowledge to technology. So we live within this society that is imbued with science. And I'm using the term science in a way, we'll look a little bit more closely at what I mean by the word science, because it's taken on many different meanings. But I'm using it in all of its different contexts presently, right? It's the body of knowledge that we have, but it's also the process of learning and understanding things about the natural world, the way that we make discoveries, and so forth. And I want you to understand that you're part of that part of science just as much as enjoying the fruits of science, okay? Because all of us, as we'll see throughout this course, all of us have a role to play in how science works within society. All of us need to develop a healthy skepticism in order to approach the information that you're bombarded with on a daily basis. And you are bombarded with more information in a day than most people would encounter in a lifetime before the Enlightenment. Right? People would go through their entire life, and what information they would come upon, either by reading newspapers or other artifacts, or conversations with people, new information, news coming from surrounding areas through word of mouth. The amount of information you are exposed to in one day is as much as most people would have encountered in a lifetime. So think about that for a second. Just how do you process all that information? How do you possibly have a filter in place, or filters in place, where you can maintain a healthy attitude towards everything that's coming at you so fast? And we're going to try to show you how we can look for some of those tools in this course. And I also want to encourage you, by the time you leave here, that you'll be an active participant in a lot of conversations and discussions that are going on in our society that are very important, and that you may not have thought involved you prior to this course. But they do. They involve all of us. So we'll talk a lot about advances in medicine and the frontiers in medicine that are going to require a lot of our societal willpower to make decisions about. We'll talk about things in physics that may happen to drive technologies to a point that could boggle our minds in the near future. We'll talk about a lot of different things, climate change and so on. We're starting with sort of an ancient question, and this isn't one that we'll address specifically, but it gives us an interesting perspective to come at this. Why science? Well, because we are curious. We want to find answers. We want to understand our natural world and our place in it. We want to understand how we can better manipulate the natural world to our ends. We've gotten pretty good at that, and now we're paying the cost for that in some ways, and we have to figure out how to fix those problems. So where did it all come from? We may never answer that question completely, but that's sort of behind what drives our curiosity. Where does it all come from? How do we fit in? How far can we go? Right? How much can we know? How much can we learn as we go forward? Now, I'll come back to at various points. I've mentioned the Enlightenment. I'm going to talk about it a lot more. It was a philosophical movement in Europe, primarily, though it was fed by a lot of scientific discoveries and research that started in the Middle East and in the Far East. And so we'll talk about the contributions that all of these world scientists, cultures around the world have made to science. There is sort of a European lens to our modern understanding of science because of the imperialism of the age, and a lot of the early scientists that we recognize come from Europe. But it's come back to a global perspective. I mean, we're back now to where science is done everywhere in the world, and what makes it work is that science is a common language. It doesn't matter what your spoken language is, it doesn't matter what culture you're living in. The science culture, the process of science is the same. It's a common language that we all share and can share around the world. And it has a rich history. A history that goes back, again, more than 300 years, though I'll throw that number out there as just a good ballpark figure. And we can recognize a lot of people along the way who have contributed major thoughts to science. There's a quote from Isaac Newton, the guy up there in the middle top row, that if he said, "If I have seen far, it is by standing on the shoulders of giants." Now, we oftentimes think of Newton as one of the first scientists, one of the most significant early scientists. And he's talking about how many people before him had made discoveries about the natural world that allowed him to make further discoveries. And certainly the ideas that Newton developed allowed Einstein to see further. And today's scientists are using the ideas that Einstein developed to look even further into the natural world and find explanations for phenomena that we observe, that we experience, and ways that we can manipulate those things. So I'm not going to make an exhaustive list of all of these scientists. You'll hear names throughout the course. We've got Galileo and Newton here, Boyle is a chemist, Darwin and Einstein. These are mostly familiar names, but these are just sort of snapshots in the history of science that we can point to by recognizing some of these ideas that these scientists have had. More than ever, though, today, science is a collaborative effort, and it always has been. That's sort of what Newton is alluding to. He has to take the knowledge of others and build on that. There used to be a little bit more of an opportunity for one individual to come up with a major breakthrough, but it's harder and harder to do as we get more and more knowledge and more specific in our professions. We work together, and again, this is globally. All right, I just went to Poland this summer. We're working with people in Poland on a lot of research. You might find I found it sort of interesting. Invasive species are a real problem. We have a number of invasive species here on the Gulf Coast that are causing a lot of problems for fisheries and industry and agriculture and so on. One of the invasive species in Poland is our crawfish. So they're studying our crawfish as an invasive species, which is sort of interesting, right? I thought that was sort of interesting. But that's just the kind of thing of how interconnected this world is. And the world has become more interconnected, as we've gone forward. Sort of, that's Disney song, it's a small world after all, right? What that means is, as we communicate more and more and our communication networks get broader, we become closer again. And so we're at a point now where our society is able to communicate globally and work globally. All right, I'm going to walk through this, but I do want to emphasize that this is just a model. Let me go back for a second. There was a title to it that might look unusual. The hypothetico-deductive model. That's another way of saying the scientific method, because the scientific method works by forming hypotheses and then deducing conclusions from experiments based on that hypothesis. So I'm going to walk through this basic outline of what this is about as good as you can get. But we're also going to spend some time talking about just how tricky it is to actually pin down a good definition of science and how science is done. There are some key points, and I'll continually make those as we go through this. But it is worth looking at this model at least to give us a basis for how to fit everything else in. And I want to point to the top because a lot of people often forget asking questions is the first step, and it's one of the most important steps. It may be the most important step, because if you don't ask a good question, you can't get a good answer. And when we talk about asking questions, these are at all different levels. You know, why is the grass green when we're kids? And I can explain that at different levels. Chlorophyll and the sun's light reflecting off, and so on, right? Why is the sky blue? Scattering of light as it strikes the molecules of the air, and so on. And we can find explanations for these things, but you have to ask the questions first. Science works by taking big questions and then breaking them down into smaller questions so that each small question can have a single answer. And that single answer has to be either yes or no. Okay? So the questions that we start with up here may come from bigger contexts, but in order for this process to work, that question has to be able to be answered yes or no. And that's one of the keys, is that no is a possibility. There can't be any wiggle room. You can't have a question that you could then qualify. If the answer comes back no, you'd say, yeah, but actually this could be true and make that not relevant. And I always use alien intervention as sort of the example here, right? If your hypothesis is that the ancient pyramids are as grand as they are because aliens intervened and helped develop the technologies, that's not a scientific explanation, because we can't test that. We can't go back in time, we can't look for the aliens. Any question or any explanation I might come up with, you would say, yes, but the aliens had this cloaking device so they never saw them, or we'll never see them, or whatever. You can always fudge around it. So I can't prove it false. So these questions are very specific based on broader contexts. We then go in and do all of the background research that is possible. We want to know everything anybody has ever thought or said about that question in the past. We do repeat experiments over and over again. As a matter of fact, that's a cornerstone in science. Being able to repeat an experiment and getting the same results is very important. So a lot of times if we find that this has been thought about before and this experiment has been done before, that doesn't mean we'll stop. We may want to do it again to make sure that that answer was correct, to test that particular answer, make sure it was done correctly. But if it hasn't been, we want to know everything around it, what might have been tried and failed. That's also important. A lot of scientists try out hypotheses and figure out things that aren't. As a matter of fact, there's a cartoon I like to show of a statue of a famous scientist who was trying to find a cure for a disease and died before he could find it. But the scientists who followed him found the answer because he had done so much of the groundwork, so much of the work that eliminated possibilities, that narrowed down the right answer, and we eventually found it. So these, a hypothesis is valuable whether it's found to be right or wrong. Those of you who've been to lab this week, you see where I'm developing that in the lab, and if you come today, we'll talk more about that. We finally get to hypotheses sort of here in the middle, and a lot of people think that's where science starts. But as I've said, you have to have a question that you can have a good hypothesis to answer. The hypothesis is the possible answer to the question. It's an educated guess. I don't mind saying that, except that I want to qualify that it is an extremely educated guess based on all of that background research and the use of logic to try to find a good explanation. And I want you to hear that term, good explanation, because the video that I may not have time to show you talks about explanation and what separates a good explanation from a bad explanation. And I'll try to talk a little bit about that myself, but I do want to encourage you to watch that video. We'll get to that eventually. But a good explanation is one that, again, that can be proven true or false. If it can't be proven false, then it's not scientific. We design experiments around that question. We want to control those experiments so that we know that the answers we find are reliable. This controlled experimentation is what a lot of people think of as the keystone of science, and it is important. But again, the falsifiability of the hypothesis itself is another keystone, and the quality of the explanation being able to be tested is another one. So there's not a single piece to this in and of itself. In fact, we can do experiments in a lot of different ways. You can do laboratory experiments with test tubes and so on. You can go in the field and make observations to test ideas. You can collect samples and bring them back to the lab. We can do a lot of things that are more modeling, done with computer models or other kinds of models, mathematical models and so on. These are all experiments, and they can all be controlled so that you look at one variable at a time. I say that we have to ask a specific question that has a yes or no answer so that we can control every variable that might play a role in that explanation. And we can test those variables one at a time and control our experiment so that we can say for sure this variable impacted this phenomena in this way. So there's a lot of constraints there that go into this, and we're going to lose sight of this very quickly because we're going to be talking about the big ideas that form the larger, context of this process. We're very rarely, other than this week's lab, going to be able to really model this process very well because we're going to be spending our time in the big ideas. But the way we got to these big ideas is by breaking them down into little pieces, testing those pieces through this process, and then rebuilding our explanations of those big phenomena, those bigger phenomena. Now I will come back to how we do that through theory. The analyzing results and drawing conclusions. Again, this is done through maybe a statistical analysis. Sometimes the answers are pretty obvious. Sometimes it requires more statistical analysis, and then you've got to make sure that that is properly applied and that those conclusions are valid. You make those arguments, and you go to meetings, and you tell people this is what you think, and they argue with you and say, no, you're all wrong. You did this wrong, you did that wrong. I'm going to do it myself and see what I get. And that goes on and on and on, and eventually this decision is sort of made. This hypothesis is true or false. It doesn't take one time through. It may take many times through to come to that conclusion. The results are reported, should be reported either way. There's a little bit of an issue in science. People don't like to report false results, but we need to know that. So people really need to explain, by the time we do publish something that turned out to be true, we have to be careful to make sure we chronicle all of the false steps as well, because that's valuable information. We need to know that. But every time we get an answer with, well, that hypothesis didn't work, we tried it over and over again, that didn't work, what other explanation could there be? How else can we answer this question? And then let's go through this again. And that's what I mentioned sometimes in finding cures for diseases. This is what has to happen. You have a disease, you think, okay, this disease is caused by a virus. We can look and we can find this virus. It's this type of virus. We might be able to stop this virus by damaging its shell, its coating. Let's try this medication. Well, that didn't work. Okay, now we can attack this virus in a different way. That didn't work, and so on. So eventually, we find ways to cure diseases, but it might take a long time. Some things go a little quicker. You get the right answer faster. Some things take longer. But it's this process, this step-by-step iterative process that goes on and on again, over again, that we have to rely upon to get this done. Okay, I want to now talk about how we get back to those big explanations, how we get back to looking at the bigger picture. So we've taken a big idea, we've broken it down into little bitty pieces so that we can start answering the questions. But part of this process is having again, keeping view of this big idea and having a way to explain that can give us those hypotheses, a tool, an engine for forming hypotheses. And what we use for that are called theories, scientific theories. And I should specify a scientific theory is a unique thing. You can use the word theory in many different ways. You could be in English class and they say, what's the theory of your paper? Meaning, what's the central idea, right? What's their central premise? Even in science, we'll use the word theory to sort of talk about those in-between ideas that are bigger than a hypothesis, but not quite the grand unifying concepts that we're talking about with scientific theories. There are really only a handful of scientific theories. We'll look at quite a few of them during this class. Quantum mechanics, special relativity and general relativity, evolution, thermodynamics, and so on. These are big ideas that explain entire fields of things. Evolution explains everything we know about biology, about our own biology and nature, and everything we observe is explained by that theory. But I want to make sure you understand too that within a theory are not only all of the observations that we've already made, all of the facts that we know, if we observe something to happen the same way over and over and over again, we call it a law, right? We have a law of gravity because we've never seen anything happen differently. If something's dropped, it falls at the same rate, and we can calculate that for different planets of different masses, and so it's very reliable observations. Our observations of gravity are extremely reliable, so reliable we call it a law. And there are laws that we then can rely upon to find explanations. So we take all of this known information, all the new data that we collect from experiments, and we use it to make predictions. And this is really what a theory is for, because we don't know everything about any of these major fields. We just don't, and we're far from knowing everything about any of these major fields, even though we know a lot, particularly after 300 years of a exponential growth of knowledge. We do know a lot, but we're just beginning. We're really just beginning to understand the world and all of its, how it works. So we need to be able to predict answers that can explain phenomena. Explanation is the goal. We want to explain what causes something to happen, cause and effect relationships, that we want to be able to explain that. And we haven't had a good way to do this for a long time. The video that with David Deutsch that I want you to watch at some point is talking about how we've always sought explanations. Ever since ancient civilizations, or even before ancient civilizations, as we emerged as Homo sapiens, consciousness that has produced art and culture and all these other patterns of things, we've always wanted explanation. We've always wanted to be able to explain why the seasons change and why some years you get more rain than others. Right? So some years your crops flourish and other years you can't grow enough to feed everybody. Why people get sick and why that seems to be, why some people get sick and other people don't. And some people get sick and die and some people get sick and get better. I mean, all of these things, why? We don't understand. We want an explanation. Prior to science, we used mythology, generally, to provide explanation. And mythologies are very useful, and they're very rich, and they do give us a lot of information about ourselves, about our world. But a lot of times it's not on a functional level. It's not about really how the seasons work. Okay, his example is the Greeks explain the seasons as Persephone's release from the underworld by Hades in the spring, allowing for the venting of heat from Hades and bringing about summer, which is it explains it fine, but it doesn't have anything to do with reality, right? I mean, there's not really a god of the underworld letting heat out in the springtime to bring about summer. It took a lot of careful observation once science came about to actually understand, okay, it's the Earth's orientation towards the sun. We're tilted on our axis, and as we revolve around the sun, our tilt remains constant, so that part of the year we're tilted towards the sun, part of the year we're tilted away. The incidence of the sun's radiation on the surface of the Earth is thus more intense when we're tilted towards the sun and less intense when we're tilted away, and it explains everything about the seasons very well. It's also what he calls a good explanation because everything has to be right or it doesn't work. Whereas in the myth you can replace, it could be Thor and Odin instead of Zeus and whatever. It doesn't matter which entities are identified in the story. You can change it all around. He mentions, for instance, that if that were the explanation and you went to Australia, you'd realize, wait a minute, it's the opposite down here. When it's summer up there, it's winter down here. When it's winter, we're back home, it's summer down here. That doesn't fit within our explanation. Well, there are ways to adjust the myth to explain that Persephone doesn't just vent the heat, but she pushes it out of her vicinity, causing summer in one part of the world and winter in another. So it's an interesting thing. You ought to watch his explanation. I paraphrased it fairly well, but I think he does a good job of building this explanation more fully. But it's what science allowed, what science really did was then provide a good explanation that can't be altered, right? I couldn't change the Earth's tilt and get the same seasons. And it's based on observations of, again, of laws that we understand. The incidence of radiation can be observed over and over again. It always acts the same way. The laws of thermodynamics can be observed and defined as laws. They can't be changed. You can't fudge with them, because then things don't work anymore, right? So we know those things, and that's something that science has provided. We are looking for a unified theory, and I want to go ahead and point that out. By the end of this class, when I talk about a unified theory, I'm not talking about all of the theories being unified, though in a sense that's true, but we're talking primarily within physics. We have theories that can explain gravity in different ways. We don't know what gravity is yet. We don't know if it's a property of a particle, such as the way light and electricity is, and other forces. We don't know if it's the momentum of space-time, which is how relativity describes it. And we have to find a theory that can unify quantum mechanics and relativity with inflation theory and these other theories in physics. Now that will then include the rest, because that's the ultimate reductionism. We've often done science through what's called reductionism. I'll get back to that in a second. Let me just mention, these are some of the theories that I've mentioned, and we will talk about about each one of these. I've mentioned thermodynamics and general special relativity, quantum mechanics. I've mentioned inflation, which replaced the Big Bang. We'll still use that term quite a bit. String theory is the next candidate and could be the unified theory we're looking for, so we'll spend some time on that. The Standard Model is also part of those, that big picture, because it describes particle physics. Evolution, plate tectonics. We'll be looking at plate tectonics first, because we're going to be talking about the Earth. And by the end of the course, you'll understand why I have this cat inside a computer. That's going to actually make sense. I don't want to foreshadow it too much, but if you know about Schrodinger's cat, you might understand where that's coming from. So we'll see. I don't know if I'll be able to really get that far or not. I've also mentioned some of these things, and here's where my term reductionism is, so that's what I wanted to get back to. I've mentioned that we're looking for explanations of cause and effect phenomena. We have to apply logical our explanations have to be logical. They can't involve aliens and other stuff. Now, we've seen over time that things that were once outside of the realm of science have been brought into it as we've learned more about the world. So again, this is something that could be different in the future. We could learn things. As a matter of fact, aliens could eventually visit us and say, oh yeah, we've been out there all this time, fiddling with you, messing with you. Now, we don't have any evidence of that, and in fact, that would be shocking to me. It would be almost like that cartoon I showed at the beginning of the dragon. But I can't say that won't happen, because it's outside the realm of science right now. If that happened and they come here, well, then all of a sudden all that stuff is within the realm of science, because we can study it. We have them. We can ask them questions. We can look at their instruments. We can study them. And we can figure out how that phenomena is happening, is occurring. But right now, an explanation that invokes an alien intervention is illogical. We don't have, that would be outside of science. Reductionism is the idea that we can take a big problem and break it down into little pieces. The best example of this is studying matter. If you look at matter, right, we've got, the room is filled with air in a gaseous state, we've got solids, but all of these things can be broken down into atoms. And we can think of an atom as a basic unit of matter. I don't have my periodic table in here. I think this is the first room I've taught in that doesn't have the periodic table in it. Each atom has a different number of protons. So even an atom can be broken down into smaller things. Protons, neutrons, and electrons. Electrons and photons are quantum particles, but protons and neutrons can be broken up into even smaller things called quarks and leptons. And inside those may be vibrating strings of energy, and that's where string theory comes in. That would be the ultimate reductionism, getting us to a point at which we can no longer get any smaller. We've gotten to the smallest thing. And the idea of reductionism is, if we can understand how things work there, I'm sort of mimicking Brian Greene, you'll see him do this later. If we can understand how things work down there, then we can say, okay, strings work this way, that's why particles work this way, and because particles work this way, that's why atoms work the way they do, and because atoms work the way they do, that's why chemistry works the way it does, and because chemistry works the way it does, that's why our physiology and anatomy works the way it does, it's the way the natural environment works the way it does, and so on. Eventually, however, we have found that there are emergent properties in nature as well that emerge from complexity. Things get so complex that you can't explain them by looking at the atoms. Our behaviors are good examples of emergent properties. I can't go into your brain and go all the way down into your atoms and say, okay, this is why you think that. Right? Your thoughts are emergent. They aren't a property of the atoms in your brain, even though the brain's atoms are what allows the brain to form these thoughts. But I can't explain your thoughts based on the atomic structure of your brain. Does that make sense? So a lot of things are emergent, actually. It's not just our own consciousness, but some other things. So we're going to look at complexity and emergence within this course, as well as a lot of the areas of reductionism that have gotten us here. All right, I might have to speed up a little bit to get to the other presentations. So let me try to get through this pretty quickly. I've pointed most of these things out. I've mentioned there are various keys to science in each of these steps. Falsifiability being, I think, the most important one to try to remember. Controlled experimentation, being able to reproduce the same results from the same experiment. These are all keys to doing science. And I'm going to skip by this one too, because this week's lab has to do with this. Science is a social process. We all have to contribute. We all have to participate. And I'll talk more about that in lab. I also want to point out, again, just as a preface of this course, we're going to be talking about a lot of applied science. Those are the sciences where we actually get a product from it, or a treatment, or something that we can actually use. But there's also a lot of importance behind pure science. The Large Hadron Supercollider that found the Higgs boson, that's pure science. We don't have an application just yet for the Higgs boson. But the science that Einstein did was pure science. We didn't have any applications of his ideas at the time, but now his ideas are behind every cell phone, computer, and everything else that we have. We wouldn't have these things today if we didn't have the pure science 50 to 100 years ago. Today's pure science will lead to things 50 years from now that we can't even imagine. So it's important that we understand how both of these areas work. Pure science is basically just because we're curious, but eventually we find applications for them. All right. I think I'm getting pretty close. I do want to point out some things that maybe it's nitpicking, but there are things that if I'm really specific to science as a way of knowing, the way we learn through science is different than the way we treat you. If you go to the doctor, he's not forming hypotheses and testing his hypothesis through controlled experiments, right? That's not how he solves a problem, or she. Sorry, don't mean to be that misogynistic. A doctor does not form a hypothesis. You don't want them to. I don't want to be in the control group and not get the right medicine. I don't want the placebo, right? You want the medicine that's going to work, so they go down a list. That's a way of solving a problem, but it's not scientific. Now, sometimes it's hard to, there are PhD MDs that are doing research, medical research. I mean, there's medical research going on, don't get me wrong, but in your treatment, a physician is not acting as a scientist. An engineer is not really a scientist. Again, it's a different way of solving a problem. They're studying physics, chemistry. They may be a chemical engineer, an electrical engineer, there's applications, but the way they solve a problem is a little bit different. Again, you don't say, we're going to put a bridge over this river. Let's form a hypothesis and test to see if that bridge is going to work. Okay, you're the first one across the bridge. You're our first test subject, right? No, you don't want to have to do it that way. You have to make sure the answers are correct before you build the bridge. So it's just a different way of solving problems. It's still applied science, but it's a little bit different. Same thing with technology. Technology is both a product of scientific investigation, but also a tool within scientific investigation. And all of those things are true. We'll talk a lot about modeling and so on. And then I do want to point out that when I talk about science having to be falsified, you have to have a hypothesis that can possibly be false for it to be science. That excludes mystical thinking from science. We cannot think of a mystical explanation as scientific. That doesn't mean that we're dismissing those explanations. We just can't approach them scientifically. Does that make sense? And again, we've seen a lot of things that were one time mystical come within the realm of science. I mean, you think about, I'll use a quote later on the course, any sufficiently advanced technology is indistinguishable from magic. If I took a calculator back to Newton, he wouldn't even be able to conceive of how it works, because there are properties within that technology that are so far beyond what he knew or can know. As brilliant as he was, perhaps one of the most brilliant minds of all time, wouldn't be able to even conceive of it. So we have brought things from the realm of mysticism into the realm of science, and that will continue, but in any present time, if we can't prove something false, it's not science. That doesn't mean that there aren't other ways of knowing about ourselves and about our world. But there's also, within this, a lot of pseudoscience. I mean, there's a lot of people trying to make things look like science that aren't. One, I guess, classic example. Did anybody go see the fake Bigfoot that the guy brought to Houston on his flatbed truck or whatever it was, and claimed he'd shot a Bigfoot outside of San Antonio? And for a while, he really tried to pull off the hoax. A lot of people have tried to pull off hoaxes like that in archaeology and things like this. And because there's enough tantalizing possibility that there is a Bigfoot out there, there's enough sort of hypotheses about Bigfoot that we're on this sort of edge of, okay, what's real and what's just pseudoscience. So pseudoscience or fake science, science that really isn't based on scientific principles, people use that all the time to try to make claims, not only about fake Bigfoots, but in advertising and political arguments. All kinds of propaganda is based on pseudoscience. So we all have to be somewhat aware of how these claims are not really science, because some people can do a pretty good job of making it look that way. All right, we've seen this, and I guess that's my last slide on this one. So now we get to this. Try to pick up where I left off. Wait a minute. Get back to the beginning. And I have 10 minutes or so to try to get through this one as well. I could do these in either order. And I think I've done them in different orders, different years that are just sort of, you just have to get, well, I won't go into that yet. The way I think, but it's not necessarily as organized as it probably should be. Natural phenomena, as I've stated over and over again, this is the goal. We want to explain natural phenomena, right? Volcanoes and earthquakes and lightning and seasons and disease and all these things. These are natural phenomena. And again, in the past we've had explanations for volcanoes that involved mystical explanations and mythologies and so forth. But we've always been sort of let down by those explanations, because they may work for 1,000 years and then all of a sudden they're violated because the actual phenomena is taking place on a time scale where it looks like there's a pattern and then all of a sudden there isn't. There's been all kinds of situations where for long periods of time we might think, oh, our explanations are working. Our rituals are working and so on, and then all of a sudden it changes and, well, we can't rely on that explanation anymore. Science gives us these reliable explanations by looking for, again, the actual patterns and so forth, and being able to find those. But I do want to point out, and I've said this, I think I said this to somebody on Tuesday, and maybe it was in lab, we're no smarter today than people have been. It was in lab, right? We're no smarter today than people were 40,000 years ago, as soon as we started painting on the cave walls of Lascaux. So that's why in the book those pictures are there. Ancient civilizations have popped up all over the world. I mean, many of them we don't hear that much about when we're watching the Discovery Channel or anything else. But I mean, and again, this is just a short list, but they popped up everywhere, right? There's no group of people smarter than any other group of people. We're going to see a lot of patterns in our own history that have led to some parts of the world being able to have a military dominance over another part of the world, or develop a technology that has given them advantages and so forth. But it's not because we're smarter. there are other reasons to this. We're just, we may feel smarter today than if we think back to some of the ancient cultures, but we're not. We're not any smarter than they were. They did some amazing things. And they didn't have a scientific method, but they had some engineering principles, and they had some astronomical observations, and they had some really good, brilliant people thinking about these patterns and coming up with some explanations that worked pretty well and did some amazing things. But again, they always collapsed. They couldn't sustain themselves, and a lot of that had to do with the not being able to predict a change in the seasons or a technology that a neighboring culture may have developed or so forth. So again, I like to emphasize these things. I even like to emphasize that the connection between science and philosophy is an interesting one. Again, philosophy can encompass both mythology and science. I have a PhD, which means it's a doctor of philosophy. Science began as philosophy, and it's somewhat separated itself only because of its uniqueness, but it is still a way of understanding the natural world, just as each of these philosophies are. And each of these cultures, again, as I've mentioned, these not only ancient cultures, but modern cultures, all of them have traditions of philosophy, of thinking about the natural world, applying reason, and coming up with some explanations that really you can see where there are commonalities through all of these, as well as different approaches that enlighten us in different ways. One of the books I read growing up, The Tao of Physics and The Tao of Pooh, it really impacted me in how connected some of these explanations were to really the way things are. And so it's interesting to see how we have had an intuitive awareness of our world all along. We just haven't been able to pin down the right explanations until science came along. And part of that is I'm going to blame the Greeks. You know what, I forgot to make this my big screen, didn't I? I'm going to blame Aristotle and Plato for a lot of for the Dark Ages in a little bit, or eventually. Okay, so philosophical thinking got us down the wrong roads quite often as well. But it really did, like I said, give us the best understanding we had. But I also want to spend some time. These are some figures that were probably, and I would say, the first scientists. And it may surprise a lot of people that they're Middle Eastern and Far Eastern, not European. The European scientists who are usually given credit for being the fathers of science, like Francis Bacon, were aware of these people and were doing similar work, and were able to take this kind of work that, nobody thought, oh, I'm a scientist at this time. Nobody was thinking, these are the principles of science that I'm going to follow. But these are some of the first people, philosophers, to apply a scientific method, to take a scientific approach, to control what they were doing, control their experimentation, breaking things down into small questions and answering those, and then building back up into big ideas. So those basic steps that we talked about were being done in the Middle East and parts of the Far East, as well as in Europe, again, during the probably 15th, 16th centuries, around that time. And we owe them, really a lot of credit. Francis Bacon wasn't so egotistical that he thought he was coming up with a new thing. In his writings, he refers to these people, but he's given credit a lot of times for actually writing down the scientific method, identifying, oh, this is what we're doing. This is what they're doing. This is the scientific method. So I like to bring that up because I want to make sure you understand. This is a global, science is not unique to any culture. It's a global process. And we've seen enlightenment through philosophy in every culture. It's all come together today into a global practice. We do, however, we will see a lens, and again, I don't want to get political or historical about the Crusades and the, a lot of the atrocities that may have led to some of these patterns. But after that point, as Europe became the dominant socioeconomic center of the world, we do see the Greek philosophies emerging as the ones we based much of our understanding on, and through a European lens. Up to this point, it was in Europe that the Enlightenment happened. And so that's really the key point. That's the key turning point where we started thinking differently. We started explaining things differently. And there is a larger context. So again, please watch the video of David Deutsch, which is on my next slide. And it's in the book. There's a link to it in the book. But let me just finish this slide and then we'll get to the quiz, because we're going to do our first quiz today. And so I've just sort of broken it down, some of the key statements that I would say sort of summarize everything that I'm talking about. Before the development of modern science, natural phenomena were explained through a branch of philosophy known as metaphysics, or also known as natural philosophy. The term science at the time simply meant knowledge of epistemological origin, meaning it was reasoned knowledge or based on observation. The scientific method turned this natural philosophy into an empirical and experimental activity, which sort of separated it then from the rest of philosophy, which is simply based on reason. It's now based on, again, experimentation and controlled thinking. So that by the end of the Enlightenment, science became not just a knowledge, not just a body of knowledge, but also a process distinct from the rest of science. So it has a double meaning now. Today we use the word science to mean both a body of knowledge. When we talk about science, we study biology, geology, those are bodies of knowledge, but also a process of discovery, a way of knowing. And this course focuses on that. Even though we're going to look at each of those bodies of science, we're going to look at some of the key features of each of those. Our real focus is the process of science. So please watch this. I normally would show this when I don't fall as far behind as I did. And there's a link to it here. This is uploaded. There's also a link in the book. So let me go to the book and open up the quiz. Now again, for being here, we'll go through this quiz together. And you can do it now if you have a smartphone or a laptop, whatever, or you can do it as soon as you leave, or later, whatever. But you'll get all the answers right because you're here. Make sense? If you're not here, those of you who are not here, can still do the quiz, but you're going to have to rely upon reading the book or reading the chapter, whatever. So that's the payoff for being here. I used to just give the quiz at the end and take up all the pieces of paper, and at the end of I ended up with a stack of quizzes. It was ridiculous. Anyway, so that's why we put it in here, and this will help us. So, true or false? I'll let you guys answer first, and then I'll give you the answer. There is more than one way to practice science. True or false? That's true, because I'm a historical scientist. I go out in the field and collect data or make observations. I don't spend most of my time in a lab. I do use microscopes to look at some of the things I collected, but it's not a pipette drill, it's not that kind of science. There's a lot of different ways of doing science, so we would say true. Okay, submit that answer. Number 2, and if I can pronounce this correctly, Ibn al-Haytham, I don't know if I pronounced that correctly or not, he was one of the first to apply the scientific method. Is that true or false?
True.
That's true. I didn't list those names. I didn't try to pronounce them all on the slide. But yes, he was the one at the top of that list. And I think the one that I usually try to pick out as the most significant. He really came the closest to being the first scientist. So we'll submit that answer as true. Causes always precede effects.
True.
That's true. Seems obvious, right? If something happens, whatever caused it has to be first. Aristotle didn't think so. Aristotle thought things in the future could come back and have causal effects in the present. So we're going to talk about how that held back science for a long time. That was one of those things, as I said, it actually led to the Dark Ages in some extent. So yes, causes always precede effects. The scientific method began with Francis Bacon. False. I would say false. Now, you could argue semantically that it wasn't written down until Francis Bacon. He's the one who really put it into sort of writing, and so in some sense he did start it, but it was being practiced, again, by some other people. So I would argue that no, it did not begin with Francis Bacon, and I would say false. Okay. Falsifiability is a key to the scientific method. True. I think it's the biggest key. Now again, the physicist, his presentation, he makes a good explanation, the most important key. They both have to be there. But falsifiability is certainly very important. It's key. So we'll say that that's true as well. And we're finished. Are you sure? Yes. Hey, look at this. We got question 1 right, question 2 right, question 3, question 4. We got them all right. Yay! If you know, so just remember, if you wrote it down, whatever, if you did it while you were here, that's great. A couple minutes over, not too bad. I'll see some of you in lab. The final lab of the week. We'll get everyone caught up, and we'll be where we need to be. All right. You get, when you go to the website, it asks you which lab you're in, basically, which CRN you signed up for, and then it gets you the book. It gets you the book. Yeah, that's right. The access code allows you to put it in your
But I'm saying you can get by access code right
Yeah, you go to the website, grtep.com, grtep.com, and plug in your access code. Okay, so let's do Blackboard, so you can get in Blackboard there. If you want to come to my office after tour, pretty much all so anyway, if you have any, take a look at it on Blackboard. Yeah, you need to go to the website and buy a book every day before you have to go to the
Okay, my situation's kind of the same. Like, how did I miss? Because I just registered for a course, but I realized my gator mail is not working.
What's not working?
My gator mail. I'm not going to send emails or something. But as for making up a lab that I missed, what?
Come today.
Well, I have a class.
Well, you won't be able to make this one up then, but just try not to miss any more. If you can miss 2 labs, then we'll not put it in after 2, then it's not working.
Okay, and then the bookstore is out of the books. So is there any way I can keep up with the homework?
Yeah, you can buy the book from the publisher.
Okay, and they'll give me an access code while I wait on the book?
You'll get it right away.
Okay, awesome.
Yeah, you just have to be able to identify, when you get the syllabus, follow that link, and they'll know you're
Okay, and so then all of our homework is going to be on
I
the
put
site?
everything in Blackboard, but really everything is embedded in the book.
Okay.
So all the quizzes and the discussion questions and all that stuff is in the book.
Okay, all right, thank you.
Okay. Yeah, I've got to sign something for her.
Yeah, we have this community lab. Is there a place to send stuff for that lab?
The M&M lab?
Yeah.
No,
No.
I need to get that from you from in lab.
Okay.
It's just in there so that you can see it in context.
The only thing we need to do are the quizzes online, the discussions
discussion
online, and is that it?
That's it. Everything else is in lab. I want you in lab to do most of it.
Can we access the quizzes without the access code?
No, you'll have to have the access code to get to it.
And when is this?
And the discussion board.
When is this?
We'll have a quiz at the end of every lecture, and it's a discussion topic for each week, basically.
So I don't know Blackboard, right?
No, that's in the book.
On the.
Okay. No, it's one of the 3 days. You come to this lecture every Tuesday and Thursday, and then you're going to come to lab on Thursday.
That's what I'm.
Right. So that's today. South 806. So when you leave here, just go straight into the other building. To the right, to the south side of the building, left to the north side of the building, and that's 806 south.
And I was in Blackboard last night, and I was able to see the syllabus. So I saw the link. So do I just I can get the link because those are just have to open it.
Okay.
So I can just.
Yeah, buy it from them. Use the link that's in the syllabus. Well, you'll be able to buy it from them. Well, really, we just went through the syllabus on Tuesday, so if you have any questions about it, then after you send an email. Because you're going to come to today's lab, so you won't miss it.
Thank you.
So, you know.
She was asking
the
that.
question.
The discussion questions are also just available from the book or the discussion questions? Okay.
It's online, right?
Yes.
Discussion board.
Right. It's embedded in the book.
I didn't get the book, I have the online access code.
Well, that'll get, that's how you get to the book, yeah.
Okay.
Let me get back to it and I'll show you.
My schedule has that my lab is on Tuesday, so does that mean that I only go to lab on Tuesday?
Right.
Okay, so.
And you came Tuesday, so you're good, right? Yeah.
When I did that yesterday and put this code in,
Mhm.
it did never give me nothing of the sort.
Well, if you want to, are you coming to the lab today or did you come?
I have this Monday.
Monday, okay. If you want to come to my office maybe this afternoon, we can we can figure it out, what's going on. Because there was a problem, a couple people were getting in and it was just giving them the top and not all the text, and that they fixed that problem, so that shouldn't be a problem. But it may just be you're not quite going to the right page or something like that, so we'll figure it out.
Okay, after I put this code
Mhm.
and it didn't take me, like I did the 1098,
Okay,
it didn't take me to the screen.
really? When you
just
clicked on
had-
1098, you didn't get this?
I didn't get that at all.
Okay,
I
what
had
did you
pressed
get?
accept or something. It didn't give me that.
Okay. Well, like I said, I think, do you have time to come to my office this afternoon maybe?
Yes, well, I have another class in here in a
Uh-huh.
minute.
Okay.
Also, I gave you my.
Yeah, I need to sign that for you, but,
Or could I go to Great Rivers Technology and do the quiz and discussion board?
no, not, you have to be able to get into the book.
Get into
Because
the
they
book.
have, they have a lot of books, so, if you want. So you will be in this specific one. Don't worry about falling behind though.
Okay.
I mean, because you can catch up as soon as we can get you in
Because I have
there.
all my answers to plug in once I do get in it.
Mhm.
Okay. Okay.